Imagine standing inside a spacecraft as it slowly lifts away from Earth. Every device around you continues its steady rhythm. The lights pulse at the same rate. The onboard clock keeps its regular beat, and your body senses no immediate change. Yet, the structure of time beneath these familiar signals no longer matches the time on the ground below. This difference reveals one of the most tested ideas in modern physics. Time does not flow at a fixed, universal rate. Time behaves differently when gravity changes. Gravity, in simple terms, describes how strongly a massive object pulls on surrounding space. Physicists explain this through spacetime, the combined structure of space and time that bends around massive objects. When Earth curves spacetime, clocks near the surface move through this curve more slowly. Farther away, where the curve is less steep, time is allowed to pass slightly faster. Early clues of this effect appeared when atomic clocks were placed at different elevations. An atomic clock uses the vibration of atoms as its internal timer. These vibrations act like a precisely tuned metronome. When two identical clocks were separated by altitude, the clock positioned higher consistently showed a small but measurable lead in time. The effect remained even when instruments were rebuilt. Spaceflight provided a broader scale for this discovery. As spacecraft gained altitude, the influence of Earth's gravity weakened. The reduced curvature of spacetime allowed time on board to progress faster than on the surface. This shift remained extremely small for human perception, yet it proved essential for accurate measurements. This is why the clocks on GPS satellites must be constantly corrected. They experience reduced gravity and rapid motion, and these two factors combine to produce time distortions that must be precisely calculated for the system to function. Everyday life offers a simpler way to think about the concept. Imagine walking up a hill while a friend remains at the base. You both measure the same passing minutes, but the gravitational difference between your two positions affects time by a microscopic amount. The effect is so small on Earth's surface that it carries no practical consequence for daily routines. However, in orbit or deep space, the same principle expands into a significant physical reality. The study of time under changing gravity became a major focus of 20th century physics. Experiments grew more sensitive, and spacecraft provided platforms for long-duration tests. Measurements confirm that time consistently speeds up with altitude. This behavior has now become a foundation for understanding how planets, stars, and galaxies influence the structure of time throughout the universe. Across large cosmic distances, massive objects bend spacetime enough to produce stronger effects. Dense stars or compact regions with extreme gravitational pull can slow time by substantial amounts. These distortions shape the evolution of galaxies and the motion of cosmic structures. These same rules apply to the entire universe, linking our human-made instruments with the largest known cosmic structures. The moment a vessel leaves Earth marks the beginning of these subtle shifts. Time remains steady for those inside, yet diverges from time on the surface. This difference grows with altitude, speed, and gravitational environment. The effect stands as one of the clearest demonstrations that time is not an isolated dimension, but part of an interconnected structure shaped by gravity and motion. Time progresses at different rates, depending entirely on the physical environment surrounding an object. This flexible nature of time is one of the most consistent findings in modern physics. The rate at which time passes depends on two measurable factors: the force of gravity and the speed of relative motion. These effects appear small near Earth, but become increasingly significant as distance, altitude, and velocity increase. Gravity influences time by changing the shape of spacetime. Spacetime refers to the combined fabric of space and time that reacts to mass and energy. When a massive body such as Earth bends spacetime, clocks located within the deepest part of this curvature tick more slowly. A clock placed on Earth's surface experiences stronger curvature than a clock positioned farther away, resulting in a measurable difference in the passage of time between the two locations. The second factor, velocity, contributes a related but opposite effect. High speed causes time to slow for the moving object when compared to an object at rest. This process, known as time dilation, follows from the absolute principle that the speed of light remains constant for all observers. To preserve this constant speed, time adjusts when objects move rapidly. This adjustment becomes noticeable when spacecraft or satellites travel at high orbital velocities. Evidence for these effects emerged through carefully controlled experiments. Atomic clocks provided the precision needed, using their extremely stable atomic vibrations to measure subtle differences. When clocks were flown on aircraft, placed in satellites, or carried aboard spacecraft, their readings diverged slightly from identical clocks kept on the ground. These differences consistently matched predictions based on gravitational strength and relative motion. A relatable example can be found in the way satellite systems maintain accurate global positioning. Satellites orbit high above the surface, where gravity is weaker, causing their onboard clocks to run faster. At the same time, the satellites move at high speed, which slows their clocks. Engineers calculate both effects to ensure the system's timing remains precise. Without these adjustments, navigation errors would accumulate rapidly. On larger cosmic scales, differences in time become far more pronounced. Regions near massive stars experience slower time due to intense curvature of spacetime. In contrast, objects traveling through low-gravity regions accumulate time more quickly relative to those within stronger gravitational fields. These variations shape the evolution of cosmic structures and help explain the motion of galaxies across vast distances. Time in space does not drift randomly. It follows predictable, consistent patterns defined by mass, velocity, and the geometry of spacetime. These patterns remain consistent from orbiting satellites to distant galaxies, revealing that time is a dynamic physical quantity influenced by the environment rather than a universal, unchanging flow. Time passes at different rates depending on the force of gravity. This connection comes from spacetime, a combined framework where space and time respond to the presence of mass. When a massive object creates a strong gravitational field, space-time bends sharply, and clocks located within that deep curve measure time more slowly. This behavior occurs consistently across objects as small as laboratory clocks and as large as planets and stars. The principle becomes clear when examining Earth's gravitational field. Near the surface, gravity is relatively strong because mass is concentrated below. A clock placed here moves through the deepest curve of spacetime. If another clock is positioned farther away from Earth, where gravity weakens, that clock experiences a shallower curve. The difference in this curvature changes the rate at which each clock measures time. Researchers confirm this effect by comparing atomic clocks at different altitudes. Atomic clocks use precise oscillations of atoms as their timing mechanism, producing extremely stable and predictable intervals. When one clock was placed at a higher elevation, it consistently recorded slightly more elapsed time than an identical clock kept closer to the surface. The difference remained small but measurable, demonstrating that gravity directly shapes the passage of time. This effect appears in everyday contexts as well, although on a scale too small for human perception. A person standing on a mountain accumulates time a tiny bit faster than someone at sea level. The difference is only a microscopic fraction of a second over an entire lifetime, yet the physics remain the same. These subtle variations become essential when considering spacecraft, satellites, or long-duration missions that move far from Earth. On larger cosmic scales, gravity's influence grows dramatically. Massive stars, dense clusters, and compact astronomical objects create regions where time slows significantly. Near extremely dense bodies, space-time curves so sharply that the local flow of time can slow by enormous factors. Observations of these environments help scientists understand how matter behaves under extreme gravitational pressure and how cosmic structures evolve. Gravity's effect on time does not fluctuate randomly. It follows precise mathematical rules that have been tested repeatedly through ground-based experiments, satellite measurements, and astronomical observations. These rules form the foundations of modern physics and provide a clear framework for predicting how time changes across different environments. The relationship between gravity and time illustrates that time is not an isolated quantity. It is shaped by the distribution of mass in the universe and changes according to the space-time curvature that mass produces. This connection explains why time on Earth, time in orbit, and time near massive celestial bodies do not progress at the same rate. The rate at which time passes changes when an object moves at high speed. This effect comes from a deep, fundamental principle. Light must travel at the same speed for everyone, regardless of their own velocity. To maintain this constant speed, time itself must adjust. When an object moves quickly, time slows down for that object, compared to one that remains stationary. This concept is known as time dilation. It appears when comparing the passage of time for two clocks following different paths. A clock that stays on Earth measures time based on Earth's relatively slow motion. A clock placed on a fast-moving spacecraft experiences vastly different conditions. The increased velocity causes the onboard clock to tick more slowly. The effect is extremely small at ordinary travel speeds, but grows as velocity increases. Early evidence came from precise measurements of unstable particles moving near the speed of light. These particles, known for their short lives, survived longer when traveling at very high speeds. Their extended lifetimes matched predictions based on time dilation. These observations demonstrated that time responds directly to velocity, even at the atomic level. Later, highly accurate atomic clocks allowed researchers to test the effect more clearly. When clocks were flown on high-speed aircraft or placed on orbiting satellites, they recorded time at slightly different rates than clocks kept stationary on the ground. The faster the clock moved, the more pronounced the slowing of time became. These results perfectly aligned with theoretical expectations, confirming the precise link between velocity and time. Everyday examples help clarify the principle. Consider two people jogging around the track. The time difference is too small to measure. However, if one person could run at a significant fraction of the speed of light, their watch would record less elapsed time compared to the person standing still. This analogy illustrates how velocity influences the flow of time without requiring dramatic effects in daily life. In the context of spacecraft and satellites, the impact becomes important. Objects in orbit move quickly enough that engineers must account for time dilation when designing navigation systems. For example, satellites in the Global Positioning System experience measurable time changes due to both their speed and their altitude. These changes must be corrected for the system to provide accurate location information. Across the cosmos, velocity plays a powerful role in shaping the flow of time. Stars orbiting the centers of galaxies move at high speeds, causing their experience of time to differ from that of slower-moving stars. Galaxies themselves travel through space at significant velocities, which contribute to variations in the passage of time on large scales. The relationship between speed and time reveals that time is not a rigid or uniform progression. It adapts to motion, adjusting in a way that preserves the fundamental structure of physical laws. This behavior reflects a universal pattern observed from subatomic particles to massive celestial systems. Time on Earth progresses at a rate shaped by the planet's gravity and its moderate speed. This stable rate forms the reliable basis for all our clocks, calendars, and daily human activity. In contrast, time in space changes according to altitude, velocity, and the surrounding gravitational environment. These differences become clearer when comparing how clocks behave in various regions near and far from Earth. At Earth's surface, gravity is strong enough to bend space-time noticeably. This deep bend causes clocks positioned close to the surface to measure time slightly more slowly than those located farther away. Even though the effect is extremely small, it remains measurable with sensitive instruments. The stability of Earth's gravitational field allows this rate to remain consistent for practical use in daily life. As altitude increases, the influence of Earth's gravity weakens. A clock placed on a high-altitude satellite experiences less curvature in spacetime. This reduced curvature allows time to progress a bit faster than it does at ground level. The difference grows with distance from Earth and becomes significant for devices that rely on precise timing, such as navigation satellites. Motion introduces another difference. Objects in orbit move at high speed relative to the surface. This rapid motion causes time to slow slightly for them compared to stationary clocks on the ground. The combined effects of reduced gravity and increased velocity determine the overall rate of time for orbiting spacecraft. Engineers must precisely calculate both influences to keep satellite systems aligned with Earth time. The comparison becomes more dramatic when looking beyond Earth's immediate vicinity. In vast, deep space, where gravitational influence is minimal, time flows more quickly relative to regions where gravity is stronger. Near massive stars or dense celestial bodies, gravity becomes strong enough to slow time significantly. Historical experiments demonstrated these preferences through repeated tests involving aircraft, spacecraft, and satellites. Each test confirmed that clocks diverge consistently depending on their environment. The agreement between theory and measurement strengthened the understanding that time is not fixed, but depends on physical conditions. An everyday analogy helps illustrate the concept. Comparing Earth time to space-time is similar to comparing two identical stopwatches placed in environments with different temperatures. The stopwatches function the same, but the external conditions influence their performance in subtle yet persistent ways. In the case of time, gravity and motion play the role of environmental factors. The contrast between Earth time and space-time reveals that time is a dynamic quantity. It responds to gravity and motion, leading to measurable differences across distances as small as a few kilometers or as vast as interstellar space. This contrast provides a framework for understanding how time behaves, not only within Earth's environment, but throughout the universe. Time slows when an object enters a region of strong gravity, often described as a gravity well. This well forms around any massive body, such as a planet, because its mass bends the surrounding space-time. The deeper an object is within this gravitational well, the slower time progresses relative to regions where the gravitational pull is weaker. This effect appears consistently across planets, moons, and other celestial bodies. Earth's gravity well provides a clear example. At the surface, the depth of the well is greatest due to the planet's concentrated mass. A clock positioned on the surface experiences this curvature directly. If another clock is placed far above Earth, where gravitational pull is weaker, the higher clock runs faster. This difference remains extremely small for practical human experience, but becomes important for precise scientific measurements. Other planets exhibit more pronounced effects. For instance, a planet with greater mass than Earth creates a much deeper gravitational well. A person standing on the surface of such a planet would experience a stronger gravitational field, causing time to slow more compared to time on Earth. Conversely, on smaller celestial bodies with weaker gravity, time would pass slightly faster. These variations follow predictable, precise patterns based on math and distance. Scientific confirmation came through multiple forms of measurement. Spacecraft traveling near large planets recorded changes in timing consistent with theoretical predictions. Observations of signals transmitted from probes also showed slight shifts in frequency as they moved closer to or farther away from massive bodies. These shifts were a direct reflection of the changing rate of time caused by gravitational strength. An
everyday analogy can help clarify the concept. Imagine walking down into a deep valley. This requires more effort than standing on flat ground because you are moving deeper into a region shaped by gravity. In a similar way, clocks positioned deeper in a gravitational well feel
the effects of stronger curvature in space-time. The result is a slower progression of time compared to clocks outside the well. On a cosmic scale, planetary gravity wells are only one part of a broad spectrum. Larger celestial objects, such as stars and dense star clusters, produce much deeper wells that slow time more dramatically. These variations influence the motion of objects and the evolution of systems spread across large distances. The behavior of time inside gravity wells shows that time is connected to the gravitational environment. It does not remain constant, but changes according to the mass and structure of the surrounding region. This relationship provides a fundamental framework for understanding time across planetary systems and across the wider universe. Time inside an orbiting spacecraft progresses at a rate determined by two opposing influences: reduced gravity and high orbital velocity. These factors act simultaneously, shaping the flow of time differently than on Earth's surface. Although the differences remain small for human perception, they become essential for scientific accuracy and long-duration missions. An orbiting spacecraft moves through a region where Earth's gravitational pull is weaker than at the surface. Because gravity shapes space-time, a weaker gravitational field allows time to pass slightly faster. A clock on board experiences this weaker gravity and accumulates more time compared to an identical clock kept on the ground. However, orbital motion introduces a second slowing effect. A spacecraft must travel at high speed to maintain its orbit, and this rapid motion causes time to slow relative to stationary observers on Earth. The result is a balance between two opposing influences. Gravity speeds up time, while velocity slows it down. The overall rate of time flow depends on which effect dominates at the altitude of the spacecraft. In low Earth orbit, such as the region of the International Space Station, the slowing effect of velocity is stronger than the speeding effect of gravity. This causes time inside the station to run slightly more slowly than time on the ground. The difference accumulates by only a small fraction of a second over months, yet it aligns perfectly with theoretical predictions. Evidence for this phenomenon comes from decades of satellite and spacecraft measurements. Atomic clocks carried aboard missions consistently show timing shifts that match calculations based on gravitational strength and orbital speed. These measurements confirm that time in orbit follows well-defined physical laws. A relatable comparison is everyday travel. When two people take different routes, their travel times differ depending on speed and terrain. Time in an orbiting spacecraft changes for similar reasons. The route through space-time varies depending on altitude and motion. The spacecraft travels along a path shaped by both weaker gravity and rapid velocity, leading to a unique and measurable time flow. This behavior extends beyond low Earth orbit. As spacecraft travel to higher altitudes, the velocity needed decreases, while the gravitational field weakens even further. At a certain distance, the speeding effect of reduced gravity finally dominates, causing time to run faster than on Earth. Deep space missions experience this environment more clearly, with clocks on board accumulating time at a slightly faster rate. The time environment inside orbiting spacecraft demonstrates that time is not universal. It responds to the specific gravitational and kinetic conditions of each orbit. These variations shape navigation, communication, and scientific observation across every mission operating above Earth's surface. Time slows significantly near massive stars, and even more near compact objects like black holes. This behavior arises from the extreme bending of space-time created by large concentrations of mass. When mass increases, the gravitational field strengthens, and the depth of the surrounding gravitational well grows. Clocks within this region progress more slowly than clocks located where gravity is weaker. A massive star provides a clear example. Its large mass bends space-time far more strongly than Earth does. A clock placed near the surface of such a star would move at a slower rate compared to an identical clock kept far from any massive body. Although humans cannot stand on these stars, observations and calculations show that time near their surfaces progresses measurably slower. The effect becomes dramatically larger around compact objects. A neutron star, which contains more mass than the Sun compressed into a small region, creates an environment where space-time curves sharply. Signals leaving the surface of a neutron star stretch as they climb out of the gravitational well. This stretching reflects the slower passage of time experienced near the star. Around a black hole, time distortion reaches its ultimate limit. A black hole forms when mass collapses into a region so dense that the curvature of space-time becomes almost vertical. At the boundary known as the event horizon, time for an object falling inwards slows down dramatically relative to distant observers. From far away, the falling object appears to move more slowly as it approaches the horizon, because time near the black hole is passing at such a different rate. Evidence for these effects comes from astronomical observations. Light signals near massive objects undergo changes in frequency known as gravitational redshift. This shift occurs because time in the strong gravitational field runs more slowly. Measurements of pulsar timing around neutron stars also confirm predictions about how mass affects the flow of time. A simple analogy helps illustrate the concept. Imagine standing on a trampoline while holding a heavy object. The heavier the object, the deeper the surface bends. Walking near the deepest part slows your movement because the slope becomes steep. In space-time, the same idea applies. The deeper the curvature, the slower time progresses for objects within that region. On cosmic scales, these differences shape the formation and behavior of galaxies. Massive black holes at galactic centers affect the motion of nearby stars and the timing of events occurring in their vicinity. The slowing of time becomes part of the structure that governs how systems evolve over long periods. Time around massive stars and black holes highlights the link between gravity and temporal flow. The strength of the gravitational field directly determines how quickly time passes, producing predictable variations across regions of different mass and density. Space-time curvature describes how mass and energy shape the very fabric of space and time. Instead of treating space and time as separate components, modern physics views them as a single, connected framework. When mass is present, this framework bends, and objects moving through it follow the paths defined by that curvature. Time becomes part of this structure, changing its rate depending on how strongly space-time is distorted. A useful way to picture this is to imagine a flexible surface that bends when weight is placed on it. A heavier object creates a deeper depression, similar to how a massive planet or star bends space-time more strongly. Objects placed near this depression follow paths shaped by the curvature. In the reality of space-time, these paths define both the movement of objects and the rate at which time flows. Measurements near Earth reveal this curvature through the behavior of clocks. Because Earth has mass, it bends space-time enough to cause time to pass slightly more slowly at the surface than at higher altitudes. Atomic clocks placed at different elevations confirm this difference by showing consistent variations in elapsed time. These variations match the predicted curvature produced by Earth's mass. The concept extends across planetary systems, galaxies, and large-scale cosmic structures. Massive planets create far deeper curves in space-time than smaller bodies. Stars create even stronger curvature, influencing the motion of nearby planets and the behavior of light passing through their gravitational fields. Observations of starlight bending around massive objects provided key confirmation of space-time curvature in the early 20th century. Space-time curvature also explains why gravity affects all objects equally, regardless of mass. Objects follow the curves of space-time naturally, without being pulled by an invisible force. This replaces the older view of gravity as a force and describes it instead as the geometry of the universe. Clocks, light, and physical processes all respond to this geometry in predictable ways. A relatable example occurs when driving along a road with gentle slopes. The car follows the path defined by the landscape, not because it is pulled downward, but because the geometry of the road shapes the route. In a similar way, objects follow space-time curvature created by math. The geometry determines both their motion and the rate at which time progresses. On cosmic scales, large clusters of galaxies bend space-time enough to slow time significantly within their regions. This curvature influences how galaxies move and how cosmic structures form over billions of years. Observations of gravitational lensing, where light bends around massive clusters, reveal the shape of space-time and provide evidence for the distribution of matter. Understanding space-time curvature clarifies why time behaves differently across various environments. Time is part of a connected structure with space, and both respond to mass and energy. This connection forms the basis for explaining time dilation, orbital motion, and gravitational effects throughout the universe. The relationship between speed and time follows a consistent physical rule. As an object approaches the speed of light, time for that object slows down relative to slower observers. This effect, known as time stretching, arises because the speed of light must remain the same for everyone, regardless of their own velocity. To preserve this constant speed, time itself must adjust in a predictable way when velocity increases. The principle becomes clear when examining high-speed particles. In laboratory settings, unstable particles travel at speeds close to the speed of light. These particles, which normally decay in a very short period, have their lifetimes extended when accelerated to high velocity. The extended lifetimes of these particles match the mathematical predictions of time dilation, demonstrating that speed directly alters the passage of time. A spacecraft traveling through space feels the same principle. At ordinary travel speeds, the effect is too small to detect without extremely precise instruments. As velocity increases, especially during long-duration missions, time slows for the spacecraft relative to clocks on Earth. The difference remains small, unless the spacecraft approaches a significant fraction of the speed of light. But it follows the same rules confirmed through experiments with particles. An everyday analogy helps illustrate this idea. Imagine two people on a moving walkway. One stands still while the other walks quickly. Although they both share the same environment, their paths through that environment differ. In the context of space-time, high-speed motion changes the path through which time is experienced, causing a measurable adjustment in the rate at which time passes. Evidence for cosmic speed limits comes from astronomical observations. Light from distant galaxies shows predictable shifts in frequency. These shifts, known as redshift or blue shift, indicate how fast the galaxies are moving and confirm that the speed of light remains constant regardless of how fast the source is moving. The constancy of light speed serves as the foundation for why time must stretch or compress depending on velocity. On larger cosmic scales, the interplay between speed and time influences the evolution of galaxies and the movement of stars. Objects orbiting rapidly around massive centers experience slower time than objects moving more slowly. These differences, while small in human terms, accumulate over millions of years and affect how systems develop. Time stretching represents a core feature of the universe. It shows that time is not independent of motion but responds directly to velocity. This behavior applies to particles in accelerators, spacecraft in orbit, and galaxies moving across vast distances. The speed of light sets the scale for how much time must change, creating a consistent framework that governs all temporal behavior throughout the universe. The human body keeps time using biological rhythms that depend on external cues such as daylight, gravity, and regular environmental cycles. When a person leaves Earth, these cues change, and the body's internal timing system responds to the new conditions. The rate at which biological processes occur remains tied to the physics of time, which shifts according to gravity and motion. But the body also adapts through its own regulatory mechanisms. A key component of the body's timing system is the circadian rhythm. This rhythm is controlled by a cluster of neurons known as the suprachiasmatic nucleus, which responds to light and signals other systems to maintain a roughly 24-hour cycle. On Earth, the cycle aligns with sunrise and sunset. In space, however, spacecraft orbit Earth quickly, causing multiple sunrises and sunsets within a single day. Astronauts rely on artificial lighting schedules to maintain a stable rhythm. Biological processes such as hormone release, temperature regulation, and metabolism depend on consistent timing. These processes continue in orbit, but must adjust to the altered gravitational environment. Microgravity reduces mechanical loads on muscles and bones, changing how the body regulates growth, repair, and energy use. Although these changes affect physical health, they occur within the same broader temporal framework shaped by the spacecraft's environment. The rate of time itself also changes slightly once the body is in orbit. Because clocks inside the spacecraft run at a different rate than clocks on Earth, the body accumulates time at a slightly different pace. The difference remains far too small for the body to detect directly, but it demonstrates that biological and physical timing are connected through shared environmental conditions. Evidence for these effects comes from long-duration missions aboard the International Space Station. astronauts undergo regular medical evaluations that track how biological rhythms adjust to orbit. Measurements show that sleep cycles, appetite patterns, and hormone levels shift in response to the space environment. These changes reflect the body's attempts to maintain stability while adapting to new timing cues. An everyday example helps illustrate the concept. Jet lag occurs when a person crosses time zones and external cues do not match internal timing. The body gradually adjusts by shifting its rhythm to align with the new environment. Spaceflight introduces similar adjustments, although the changes are more complex because the environmental cues differ fundamentally from those on Earth. In deep space, where sunlight patterns and gravitational influences differ even more, the body's reliance on artificial timing becomes essential. Without consistent external signals, biological rhythms depend entirely on controlled light cycles, activity schedules, and monitoring systems. These tools ensure that essential processes remain synchronized. The behavior of the body's clock beyond Earth shows that biological timekeeping responds to environmental structure. While the body maintains its internal rhythm, the passage of time itself follows the physical conditions of space, linking human physiology with the broader behavior of time in the universe. Global Positioning System satellites operate in an environment where both gravity and velocity alter the rate at which time passes. Because the system depends on precise timing signals to determine location, even small differences in time flow cause measurable errors. Engineers must account for these distortions to ensure that navigation remains accurate. GPS satellites orbit far above Earth's surface, where gravity is weaker. In this region, space-time is less curved, and onboard clocks run slightly faster than clocks on the ground. This gravitational effect increases the rate at which time passes for the satellite. At the same time, satellites travel at high orbital speed, which slows their clocks due to velocity-based time dilation. The combination of these two influences determines the net rate at which satellite time progresses. Gravitational effects dominate at GPS altitudes. As a result, satellite clocks run faster relative to those on Earth. Engineers calculate this difference precisely and adjust the satellite clocks before launch so that they remain synchronized with ground-based time once in orbit. Without this correction, errors in satellite timing would accumulate by several microseconds each day. These timing errors would produce significant navigational inaccuracies. GPS determines location by measuring how long it takes for signals to travel from satellites to receivers on Earth. Because radio signals move at the speed of light, even a small timing error changes the calculated distance by a large amount. For example, a microsecond of error corresponds to hundreds of meters of uncertainty. Uncorrected satellite clocks would quickly make the system unusable. Evidence for the need for time correction appeared early in the development of satellite navigation. Tests with orbiting clocks confirmed that time drift occurred exactly as predicted by gravitational and velocity effects. Engineers incorporated these findings into the design of GPS, ensuring that each satellite's clock accounts for the environment in which it operates. A helpful everyday analogy is found in coordinating watches among people moving at different speeds. If one person runs while another walks, their watches remain accurate. But if tiny distortions existed at high speeds, adjustments would be necessary to keep the time consistent. GPS satellites require constant alignment for a similar reason. Their environment causes time to drift. Ground stations monitor the health of satellite clocks and upload corrections when necessary. These adjustments ensure that the timing signals remain accurate to within nanoseconds. The entire system relies on this precision to provide reliable navigation for aircraft, ships, vehicles, and smartphones. Satellite time corrections reveal how sensitive modern technology is to the structure of space-time. The predictable differences in gravitational and velocity environments demonstrate that time does not flow uniformly. Instead, it changes according to physical conditions, requiring continuous calibration for systems that depend on absolute accuracy. Human space missions provide direct evidence that time passes differently in orbit compared to Earth's surface. The environments encountered during spaceflight, reduced gravity and high orbital speed, produce measurable relativistic effects. Although these changes remain far too small for astronauts to notice, sensitive instruments confirm that time accumulates at a slightly different rate during missions. When astronauts travel in low Earth orbit, they experience weaker gravity than on the surface. This reduced gravitational field allows time to pass more quickly for them relative to observers on the ground. At the same time, the spacecraft travels at a high velocity to maintain its orbit. The rapid motion slows time slightly for the astronauts. The net effect results from the balance between these two influences. In low Earth orbit, the velocity effect dominates. As a result, astronauts aboard the International Space Station accumulate slightly less time than people on Earth. Over a 6-month mission, the difference amounts to only a fraction of a millisecond. The effect is small but measurable, and it matches predictions based on the equations of relativity. One of the most well-known studies examining time differences in spaceflight involved comparing the physical and biological changes in astronauts across long missions. Although the primary purpose was to monitor health, the data included precise timing measurements. These measurements confirmed that relativistic effects occurred exactly as expected during extended space travel. An everyday analogy can help clarify the concept. When two people take different paths during a long walk, their step counts differ slightly, even if they end at the same location. In a similar way, astronauts follow a different path through space-time, shaped by gravity and motion. Their accumulated time differs slightly from that of people who remain on Earth. Space agencies track these differences using highly accurate atomic clocks aboard spacecraft and at ground stations. Timing data from missions consistently show that clocks in orbit diverge from Earth based on well-established physical rules. These results support the broader understanding that time responds to gravitational and kinetic conditions. As missions extend farther from Earth, these effects become more pronounced. Spacecraft traveling to the Moon or Mars enter regions with different gravitational strengths and different orbital speeds. Each environment produces its own pattern of time flow. Future missions involving long-duration travel or deep space habitation will require careful timing calibration to maintain synchronization with Earth. Human missions demonstrate that time is not an abstract concept disconnected from physical experience. Instead, time is a measurable quantity shaped by the environment through which astronauts travel. The consistent results from spaceflight experiments provides strong confirmation that relativity governs time across all scales, from human missions to the broader behavior of the universe. Earth's gravity provides a stable reference that defines the rate at which time passes for most human activity. Because the planet has a consistent mass and produces a predictable gravitational field, time on the surface progresses at a steady rate. This stability allows clocks, calendars, and technological systems to operate reliably. The surface environment becomes a natural baseline against which other time environments in space are compared. The gravitational field near Earth's surface bends space-time enough to influence the rate of time flow, but the curvature remains uniform across most inhabited regions. As a result, clocks in everyday use experience nearly identical conditions. Whether a person is walking in a city or standing in a rural area, the gravitational difference is too small to create noticeable changes in time. This uniformity makes Earth an effective anchor for coordinating timing systems. Measurements using atomic clocks confirm the consistency of Earth's gravitational influence. When two identical clocks operate at the same elevation, they remain synchronized over long periods. Small differences appear only when one clock is placed at a higher altitude, because the weaker gravitational field causes time to run slightly faster. These differences follow predictable rules and reinforce the idea that Earth's gravity sets the reference for surface time. Technological systems rely on this gravitational environment. Power grids, communication networks, and transportation systems use time signals that assume Earth's steady flow of time. Because the surface environment is stable, these systems remain synchronized across long distances. Time signals broadcast from ground stations form the backbone of global coordination. An everyday example illustrates how Earth's gravity acts as an anchor. People set their watches to match local time, knowing that clocks operate at the same rate regardless of small differences in elevation. This shared reference allows schedules, transportation, and communication to remain consistent. The uniformity of gravity ensures that timekeeping devices run in harmony. When spacecraft leave Earth, the gravitational reference changes. The farther the spacecraft travels, the weaker the influence of Earth's gravity becomes. In orbit or deep space, clocks begin to drift relative to those on Earth because they experience different gravitational curvature. This divergence does not indicate that one clock is malfunctioning. It reflects the change in the underlying structure of spacetime. Because Earth provides a stable time anchor, space missions frequently synchronize their clocks with Earth-based time before departure. Ground stations monitor time drift throughout the mission and provide corrections when necessary. This practice ensures that spacecraft remain connected to the reference frame used for communication and data analysis. Earth's gravitational field establishes the baseline for how humans define and measure time. Its consistency allows scientific instruments, global systems, and daily activities to operate with precision. The contrast between Earth's stable time environment and the variable conditions found in space highlights the dependence of time on gravitational structure. Human civilization depends on the assumption that time flows at a consistent rate. Daily schedules, scientific measurements, transportation systems, and communication networks all rely on the stability provided by Earth's gravitational environment. Because gravity near the surface changes very little across inhabited regions, time remains uniform enough to support large-scale coordination. Accurate timekeeping began with simple, mechanical clocks, which relied on regular motion to mark equal intervals. These early devices worked effectively because Earth's gravitational field was stable. As technology advanced, timekeeping shifted to quartz oscillators and then to atomic clocks. Atomic clocks measure time using the vibration of atoms, which remain extremely stable under constant environmental conditions. These clocks form the basis for international time standards. Earth's gravitational environment ensures that the rate of time measured by these clocks remains consistent. When clocks operate at the same elevation, they follow nearly identical rhythms. Global time standards, such as Coordinated Universal Time, rely on this uniformity. Dozens of atomic clocks around the world compare readings continuously, and small differences are averaged to maintain a precise global time reference. Technological systems depend on this precision. Power grids require synchronized timing to maintain stable distribution. Telecommunications networks coordinate signals across continents using time references accurate to billionths of a second. Transportation systems, including aviation and rail networks, follow schedules built on the assumption that clocks measure time consistently across long distances. An everyday example illustrates how deeply civilization depends on stable time. When people meet at a specific hour, they assume their clocks agree. This agreement enables coordinated work, communication, and social activity. Without consistent time, basic interactions would become unreliable. The stability provided by Earth's environment ensures that timekeeping remains dependable for billions of people. Scientific research also relies on precise timing. Experiments involving particle accelerators, astronomical observations, and satellite tracking require synchronized clocks. Because Earth's gravitational field provides a stable reference, these activities can maintain accuracy across long durations. Time differences appear only when instruments operate at different altitudes or velocities, and these effects are accounted for through calibration. When spacecraft operate outside Earth's gravitational environment, their clocks drift relative to ground-based time. Engineers compensate for this drift to ensure that navigation and communication remain aligned. The need for these adjustments highlights how central Earth's stable time environment is to human systems. Civilization's dependence on stable time reflects the connection between physical conditions and societal structure. The predictable flow of time on Earth allows technology, communication, and daily life to function smoothly. As humans expand into space, maintaining this connection will require new systems capable of adapting to time environments beyond the planet's surface. Time during deep space travel progresses according to the gravitational and velocity conditions encountered far from Earth. As a spacecraft moves away from the planet, the influence of Earth's gravitational field decreases. This change alters the rate at which time flows on board relative to time on the surface. The effect remains small during short missions, but becomes more pronounced as distance and duration increase. In deep space, gravity from nearby bodies becomes weaker, and space-time curvature decreases. A clock operating in this environment accumulates time slightly faster than an identical clock kept on Earth. Because the decrease in curvature is gradual, the time difference grows steadily over long distances. Spacecraft traveling between planets experience these changes as they move from one gravitational region to another. Spacecraft speed introduces a second influence. Long-distance missions require sustained velocity to move efficiently between celestial bodies. High velocity slows the progression of time on board relative to Earth. The balance between reduced gravity and increased speed determines the overall rate of time flow. Missions with faster trajectories experience stronger velocity effects, while slower-moving missions experience greater influence from weakened gravity. Evidence for these effects comes from data collected during interplanetary missions. Signals sent by spacecraft traveling to Mars or beyond show predictable timing shifts caused by changes in gravitational strength and motion. Ground stations monitor these variations to maintain accurate navigation and communication. The measured shifts confirm theoretical models describing how time behaves outside Earth's gravitational environment. An everyday analogy helps illustrate the concept. When two people travel along different roads at different speeds and elevations, they cover distance in distinct ways, even if they start and end at the same points. Deep space travel introduces similar differences in the path through space-time. Each region along the journey shapes the rate at which time passes. As missions extend farther from Earth, the cumulative effect becomes more significant. A spacecraft traveling toward the outer planets encounters weaker gravitational fields and long periods of sustained motion. These conditions create measurable differences between the spacecraft's clock and Earth-based time. Although small, these differences are important for scientific measurements, data transmission, and mission planning. Future interstellar missions would amplify these effects. Traveling at a significant fraction of the speed of light would slow time on board dramatically compared to Earth. Meanwhile, the near absence of strong gravitational fields in interstellar space would allow time to accumulate more rapidly when the spacecraft is not accelerating. The combination would produce unique time environments across different phases of the journey. Time in deep space travel shows that temporal flow depends on the structure of the universe along the path of motion. Each region's gravitational and dynamic characteristics shape the accumulation of time, creating predictable differences between travelers and observers who remain on Earth. Time drift over long cosmic durations reflects how small differences in gravity and velocity accumulate across vast intervals. Even when the differences in time flow appear insignificant in a short period, they gradually build into measurable gaps over millions of years. This accumulation demonstrates that time is not uniform across the universe, and that its rate depends on physical conditions that vary from one region to another. A clock located in deep space, far from strong gravitational sources, experiences a slightly faster progression of time than a clock on Earth. The difference is extremely small on a daily scale, but becomes substantial when extended across long periods. Over millions of years, the faster clock gains a significant lead. This effect follows predictable mathematical patterns derived from the curvature of space-time. In contrast, clocks near massive structures accumulate time more slowly. Regions surrounding large stars, dense clusters, or compact objects create deeper curvature in space-time. A clock operating within these regions progresses at a slower rate. If two identical clocks begin simultaneously, one near a massive star and one in a low-gravity region, they diverge over long durations, with the distant clock recording more elapsed time. Astronomical observations provide evidence for this drift. Signals from distant galaxies reveal timing patterns influenced by the gravitational environments through which they travel. Pulses, which emit regular pulses, serve as natural cosmic clocks. The timing of their signals helps scientists understand how gravity and motion affect the passage of time over large scales. An everyday analogy can be found in two people walking different routes. If one route includes hills and uneven terrain, while the other is flat, the difference in effort accumulates over the course of a long journey. Similarly, time progresses at different rates depending on gravitational conditions. Over vast cosmic intervals, the differences grow large enough to be measurable. The movement of galaxies across the universe also contributes to time drift. Galaxies travel through regions with varying gravitational strengths and different velocities relative to one another. Each environment shapes how time accumulates. Although the differences remain small for any single moment, they introduce long-term divergence across billions of years. These time variations influence the evolution of cosmic structures. Processes such as star formation, orbital decay, and galactic rotation follow time rates that differ from one region to another. Understanding these differences helps astronomers model the long-term behavior of the universe with greater accuracy. Time drift over millions of years highlights the cumulative nature of relativistic effects. Even when changes are imperceptible over short intervals, they follow strict physical rules that become meaningful across cosmic durations. This behavior demonstrates that time is not a universal constant, but a quantity shaped by the gravitational and dynamic environments through which it flows. Different regions of the universe experience time at different rates because gravity and motion vary across cosmic structures. Each location follows its own relationship between mass, velocity, and the curvature of spacetime. This variation creates a universe in which time is not uniform, but depends on the physical environment of each region. Areas with weak gravitational fields allow time to progress more quickly. In deep intergalactic space, far from stars, planets, or
clusters,
space-time curvature is minimal. A clock placed in such a region accumulates more time compared to one near a massive object. The difference remains imperceptible on human scales but becomes significant when extended over long durations. Regions near massive bodies experience the opposite effect. A star, planet, or dense cluster bends space-time enough to slow the passage of time. The deeper the curvature, the greater the slowing. A clock near the surface of a large star runs more slowly than a clock located far away. This effect follows predictable mathematical rules and contributes to the structure of orbital systems. Galaxies illustrate how these time differences coexist on large scales. At the center of many galaxies lies a supermassive black hole, a region where gravitational curvature becomes extreme. Time near this center progresses more slowly than time in the outer regions of the galaxy. Stars orbiting closer to the center experience different temporal environments than those located farther out. Motion adds another variable. Objects moving rapidly through space accumulate time more slowly and objects moving at lower speeds. Different parts of galaxies rotate at different velocities, creating additional variation in the flow of time across their structures. These differences shape how galaxies evolve and how stars age within them. Astronomical observations provide evidence for this non-uniformity. Signals such as starlight and pulsar emissions reveal timing patterns influenced by the varying gravitational and dynamic environments through which they travel. These patterns help scientists map the distribution of mass and understand the long-term behavior of cosmic structures. An everyday comparison helps clarify the concept. When people travel through areas with different terrain, their movement changes depending on slope and surface. Over time, the differences accumulate. In the universe, each region presents its own gravitational and kinetic conditions, leading to a distinct rate of time progression. The idea that every region runs on its own clock does not imply disorder. Instead, it reflects a consistent set of physical laws. Time adapts to the structure of space-time in each location, producing predictable differences across environments. This behavior shows that time is not a single universal rhythm, but a quantity shaped by the landscape of the cosmos. Future technologies explore the possibility of manipulating environments in ways that indirectly influence the flow of time. Because time responds to gravity and motion, any technology capable of altering these factors could change how time progresses within a controlled region. While no device can directly modify time itself, engineering methods that affect space-time conditions may produce measurable temporal shifts. One area of research involves the development of advanced propulsion systems. Faster spacecraft generate stronger velocity-based time dilation. If propulsion systems allow travel at a significant fraction of the speed of light, the passage of time aboard such spacecraft would slow compared to time on Earth. This effect would not require new physics. It would extend principles already confirmed through particle accelerators and high-speed satellites. Another concept focuses on artificial gravity. Creating controlled gravitational environments using rotation or engineered structures could influence how time flows within a spacecraft. Although rotational systems do not generate true gravitational fields, future technologies may explore ways to manipulate mass distribution or use concentrated energy fields to mimic gravitational curvature more directly. These methods would alter local space-time conditions and create observable changes in time progression. Studies of high-energy fields also contribute to this area. Extremely dense energy concentrations curve space-time similarly to math. Future experiments involving advanced magnetic or electromagnetic systems may reveal ways to shape space-time on small scales. If such techniques become practical, they could produce controlled variations in time flow, although the effects would likely be minimal compared to natural gravitational sources. Large-scale engineering projects in distant eras may explore even more ambitious approaches. Structures built near massive objects, such as the outer regions of black holes or neutron stars, would operate in environments where time naturally slows. Placing research stations in these areas could allow scientists to study extreme time behavior directly. However, the engineering challenges associated with such environments remain substantial. An everyday comparison helps illustrate the idea. People adjust their environment to control temperature, sound, or pressure. Although they do not alter the fundamental laws behind these quantities, they create conditions that change how those quantities behave. Future technologies may operate similarly, with time modifying the environment so that time progresses differently without violating physical laws. Scientific discussions about controlling time flow remain grounded in established principles. Time changes only when gravity or motion changes, and both follow strict physical rules. Technologies capable of influencing these factors would not override the structure of spacetime, but would work within it. Their effects would arise from precise engineering rather than direct manipulation. The study of future time-related technologies highlights the link between temporal behavior and the physical environment. While complete control over time remains beyond current capability, advancements in propulsion, energy manipulation, and gravitational engineering may produce environments where time flows at rates different from those on Earth. Time, when viewed on a cosmic scale, becomes a quantity shaped by gravity, motion, and the structure of space-time rather than a universal rhythm. Each region of the universe follows its own pattern of temporal progression, influenced by mass distribution and velocity. Understanding time in this broader context reveals how deeply it is connected to the physical landscape of the cosmos. On Earth, time appears steady because the planet's gravitational field is stable, and human experience remains confined to a narrow range of conditions. This creates the impression that time flows uniformly everywhere. When observations extend beyond Earth, the differences become clear. Clocks in orbit, near massive stars, or in deep space follow distinct temporal rates determined by their environments. Cosmic structures highlight these variations. Massive bodies, such as stars and black holes, create strong curvature in space-time. Time near these structures slows measurably compared to regions where gravitational fields are weaker. Light signals traveling near these massive objects experience shifts in frequency, providing evidence that time behaves differently depending on location. Motion contributes another dimension. Galaxies rotate at high speeds, and stars orbit their centers at varying velocities. Each motion pattern influences the rate of time accumulation. Over millions of years, these small differences create measurable divergence in the passage of time across galactic regions. The universe contains countless such variations, each tied to the movement and distribution of mass. Observations of distant objects deepen this understanding. Light reaching Earth from remote galaxies carries information about the timing of events that occurred long ago. Because the expansion of the universe stretches these signals, the timing patterns provide insight into how cosmic conditions have changed across vast distances. This information helps scientists reconstruct the history of the universe and understand how time behaved under earlier physical conditions. An everyday comparison helps clarify the idea. When several people walk different paths with unique slopes and surfaces, they reach their destinations at different times, even if they begin together. Their experiences differ because the terrain shapes their movement. In the universe, gravity and motion shape the terrain of space-time, determining how time passes for everything within it. On the largest scales, time becomes a tool for understanding cosmic evolution. Star formation, planetary growth, and galactic behavior unfold differently depending on local gravitational conditions. By measuring how time varies across regions, scientists gain insight into the age, structure, and dynamics of the universe. Viewing time from the cosmic perspective reveals it as a flexible quantity, inseparable from the structure of spacetime. It is shaped by math, influenced by motion, and expressed through the interactions of celestial systems. This understanding shows that time is not an independent backdrop, but a physical phenomenon woven into the fabric of the universe.